So chapter 8. Yeah, but you're going to like it. So this is 8.2a. We're going to take the limit as x goes to 0 of the sine of 5x over x. So this is a little bit strange. We're going back to limits. So this is like the beginning of the year, just taking a limit. Okay, limit laws. How do you feel about that on this problem? Won't work. Why? Because the bottom comes out to 0, right? So you could try limit laws, but there's a limit law that says you can take the limit of the top separate from the limit of the bottom, unless the bottom comes out to 0. So in this problem, you could try taking the limit of the top and the limit of the bottom separate, but the limit on the bottom comes out to 0, so that means limit laws don't work. Okay, so that's called an indeterminate form. So when you take the limit of the bottom, you get 0. And also, the sine of 0 is 0. So if you take the limit of the top, you also get 0. So this is called an indeterminate form. Because you know nothing when you get that. Indeterminate means cannot be determined. You know nothing. And it's tempting to say that the limit doesn't exist when this happens. Because sometimes limits don't exist, right? But you don't necessarily know that here. Just because you got 0 over 0, that does not mean that the limit doesn't exist. It means that you have to try something else besides the limit laws. Okay, so remember that list of 8 things to try? It's been a long time. But there was rationalizing and factoring and clearing double fractions. We learned lots of different ways to calculate limits. So today we get our last way of calculating a limit. It's called L'Hopital's rule. And it's spelled like this. I've seen it without the S sometimes and with the S sometimes. I think it depends on how it's a French guy. So I think it's acceptable to put either one. I like to put the S in because then it looks like hospital. But it's pronounced L'Hopital. Okay, so the way L'Hopital's rule works is you take the derivative of the top and the derivative of the bottom separately. So you don't do quotient rule. You're not taking the derivative of this whole thing. You're just taking the derivative of the top and the derivative of the bottom. Okay, so the derivative of the bottom is easy, so I'm just going to put 1 down. The derivative of sine of 5x is cosine of 5x, and then multiplied by 5, because of chain rule. And then you take the limit as x goes to 0 of that instead. Okay, so the L'Hopital's rule says if you're calculating a limit and you get 0 over 0, you can do this instead. You can take the derivative of the top and the derivative of the bottom separately and take the new limit instead. Okay, so then you just do limit laws on this. So limit laws on this, the cosine of 0 is 1. So the top is going to be 5 times 1. So the final answer to the limit is 5. Okay, so let's write down what L'Hopital's rule says. So L'Hopital's rule says if you use limit laws to try to find a limit, and you get 0 over 0, so it's important that you check to see if you get 0 over 0, because L'Hopital's rule, you can't use it until you get this form. Okay, so if you use limit laws and try to find a limit and get that, then it turns out that the limit of f of x over g of x is equal to the limit of f prime over g prime. And I should mention that you can also use L'Hopital's rule if you get infinity over infinity. Yes?
You only use it if you're taking the limit as x equals 0.
No, this is an a. So x could be approaching anything. Good question. There is a line on that, which you might not have noticed. That's not just x approaching 0, is what he was asking. Good. Okay, so let's try this one. Let's say we have the limit as x approaches infinity of x squared plus 2x over x cubed. So you could try limit laws, right? And when you take a really big number cubed, you get a really big number.
Pardon the interruption. Who's ever parked in spot 479, can you please come out to your vehicle? Thank you.
That doesn't sound good. Okay, so we took a really big number and cubed it, right? And that's going to be a really big number. And then we took a really big number squared plus 2 times a really big number. So that's a really big number. So we're trying limit laws and we're getting infinity over infinity. So that means we're allowed to use L'Hopital's rule. So in example 1, we tried limit laws and we got 0 over 0. And you're allowed to use this rule in that case. This time we're trying limit laws and we're getting infinity over infinity. You're allowed to use this rule in that case as well. Okay, so what you do is you take the derivative of the top and the derivative of the bottom separately, which is kind of weird. And then you take the limit of that new thing. And L'Hopital's rule says that the limit of this thing is going to be the same as the limit of this thing. Okay, but then you try limit laws again, and you're still getting a really big number on the bottom. and a really big number on the top. So you're still getting infinity over infinity. So you can do L'Hopital again and take the derivative of the top and the bottom separately. So derivative of the top is now 2. Derivative of the bottom is now 6x. And L'Hopital's rule says that the limit of this mass is going to be the same as the limit of this mass, which is the same as the limit of this mass. So instead of calculating the limit of this mass, we can do the limit of this mass, and we should get the same answer. That's what the rule says. Okay, so now we have 2 divided by a really big number, right? And what does 2 divided by a really big number get close to? Close to 0, right? If you take 2 divided by 1,000, it's 0.002. Or 2 divided by 10,000 is 0.0002. So this is getting close to 0, so the answer is 0. Okay, let's try. Limit as x goes to 1 of x cubed minus 3x plus 2 over x squared minus 2x plus 1. So we could try limit laws, right? The bottom is 1 squared, which is 1, minus 2, which is negative 1, plus 1, which is 0. So the bottom's coming out to 0. And 1 cubed is 1, minus 3 is negative 2. Yes? I'm not plugging the number in. I'm doing this really quick. This is a great question, Ashley. Yeah, she's suspicious because she's saying, wait a minute. When you're taking a limit, you're not supposed to be plugging a number in, right? You see why she's saying that? So I'm not doing that. I'm doing this. You see why I didn't want to write it? That's what I'm doing. Bunch of limit laws, right? And the limit of 1 is 1. And the limit of x is 1. And the limit of 2 is 2. And the limit of 1 is 1. And 1 squared is... You with me? Good. So then because I don't want to write all that stuff, it kind of looks like I'm plugging the 1 in. But really I'm doing a bunch of limit laws. Great question. Okay, so the bottom comes out to 0, and the top comes out to 0, right? So I got 0 over 0. Why am I happy about 0 over 0? I mean, if I get 0 over 0, I know nothing, right? Why am I happy about that particular knowing nothing? Because this new rule applies now, right? So instead of taking the limit of this mess, I can take the limit of this mess. But then I do try limit laws on that, and I get 0 over 0 again, right? But that's okay. Even though I still don't know anything, I can use L'Hopital's rule again. So then that's the same as the limit as x goes to 1 of 6x over 2 And now limit laws will work on this. The limit of 2 is 2, the limit of 6 is 6, the limit of x is 1. So the final answer to the limit is 3. Yes?
What if you do it, like, after you take the derivative once or twice and you get a number, like, or a number larger than 0?
Then L'Hopital's rule doesn't apply.
Then you have to do, like,
Something else. Good. So L'Hopital's rule only applies in these cases. So you have to verify that you're getting these things before you use it. That's the danger of it. You might accidentally use it when you're not allowed to. Okay, so why do you think I waited a long time before I taught you this rule? Because it's really nice, right? First of all, we couldn't have done it in chapter 2 because we didn't even know what a derivative was, right? Okay, so that's why I definitely waited after chapter 2. Okay, then why did I wait longer after that? We learned derivatives in chapter 3, so I could have taught you this, I guess, in the middle of chapter 3, so I waited longer on purpose. Yeah. So we didn't mix it up with the quotient rule, right? This is weird that we're taking the derivative of the top and the bottom separately. You're not allowed to do that if you're taking the derivative. And before you solidly, in your head, you still sort of believe that the derivative of two things divided should be the derivative of the top divided by the derivative of the bottom, right? It seems like still like that should be the case. It's not the case. I'm not changing that today. I'm not saying anything about derivatives today. When you take the derivative of two things divided, you still have to use quotient rule. But here we're just taking the limit of two things divided. And it turns out that in a few special cases, when you're taking the limit of two things divided, you can do this snazzy thing that doesn't even have anything to do with the derivative, except the fact that you're taking the derivative of top. You've got my point, right? So please do not abolish quotient rule in your head. I'm not abolishing that today. I'm just teaching you a new trick on how to calculate limits. All right, let's see. Here's example 4. This is the limit as x approaches pi of cosecant of x divided by 1 plus cotangent of x. So this is a little bit hairier because it's got trig in it. Anytime we got trig in the problem, makes it a little bit tougher, but still not going to be too bad. So let's look at our unit circle so we can try to figure out, we're trying limit laws here. Pi's over here. It's the point -1, 0. So let's see, cosecant is the reciprocal of sine. 1 over sine is cosecant. So if I take the sine of pi, that's 0. So I'm getting close to 0 if I take 1 over sine. Okay, so I've got, but then cosecant is 1 over that, right? So it's 1 divided by a number close to 0. So that's like 1 divided by 0.01. So that's getting really big. So the limit on top is getting close to infinity. If I pick something close to pi, then the sine is going to be close to 0, and then 1 divided by something close to 0 is really big. That's why I put an infinity there. Okay, then for cotangent, tangent is 1 over tangent. Sorry, cotangent is 1 over tangent. And the tangent of pi is y over x, so that's 0. So the tangent is getting close to 0. And so it's also true that 1 over the tangent then is getting close to infinity. So this is infinity over infinity. Yes? Well, I'm approaching pi. Well, because I'm taking a limit. And a limit is something close to the number, not the number. I just didn't want to write down 1 over 0 because that doesn't make any sense. But 1 divided by something close to 0, that's going to infinity. Because of what Ashley reminded us about, right? That we're not actually plugging the number in, we're plugging something close to it in. Good. Okay, so why did I go through all that logic? Why did I care what was going on over here? Because I had to make sure that L'Hopital's rule applied, right? I can't just apply the rule when it doesn't work. So L'Hopital's rule, you have to verify that you're either getting 0 over 0 or infinity over infinity before you can use it. So that's why I'm writing this down over here, just to verify. Oh, okay, good. I'm allowed to use L'Hopital's rule. So that means I take the derivative of the top and bottom separately. Okay, so derivative of cosecant is negative cosecant times cotangent. And the derivative of 1 is 0. The derivative of cotangent is negative cosecant squared, I think. Am I remembering that right? Check my notes, I guess. Oh yeah, I'm good. I was 99% sure, but you know, 7:50 in the morning. Everybody okay? Okay, so that's nice, because then one of these cosecants is going to cancel with one of these cosecants. So I've got cotangent over cosecant. And then I'm going to try to simplify that. Cotangent is cosine over sine. So I just rewrote cotangent in a different way. It's cosine over sine. And then I'm dividing by cosecant, right? And cosecant is 1 over sine. So I'm dividing by 1 over sine. So this right here, cotangent, is this. And cosecant is that. And I'm dividing them. Okay, then how do you divide fractions? You keep, change, flip, right? So that's the limit as x approaches pi of cosine over sine times sine over 1. So that's nice because the signs cancel. So we're really just taking the limit as x approaches pi of cosine. And then as x approaches pi, cosine gets closer to -1. So the final answer here is -1. Okay, so the main purpose of today is we have this list of 8 ways to calculate limits, not derivatives. We're going way back to chapter 2. We have a big long list of 8 ways to calculate limits. Now we've got number 9 at the bottom, which is L'Hopital's rule. AB, you're done. BC, here's next problem. But before we get into this problem, let's acknowledge how L'Hopital's rule is going to help in BC stuff. Even last week, you got, when you were doing limit comparison test, you may have gotten limit of t squared plus 2t plus 1 over 3t squared plus something else going to infinity. And I said, we're going to have to make a table on that to some of you. Now you can just use L'Hopital's rule. So it comes up in a lot of the limit comparison tests and divergence tests when you're taking limits. There's a lot of limits in BC, right, as x goes to infinity. So L'Hopital rule applied to all of that. This is the one thing that I'm not happy about as far as like teaching all this BC stuff first. It doesn't work for that. Well, it's really hard too, but that's beside the point. I have to do that. But that loophole of not having L'Hopital's rule was painful for me. There were 7 times when I was at the board and wanted to use L'Hopital's rule. It was painful for Zach as well. He wanted to use L'Hopital's rule all the time. So don't forget about it when you're doing BC stuff. It's a big deal. It'll help you a lot. Okay, so we're going to take this limit, and let's try limit laws. So this is getting close to what? X is getting close to infinity, right? And then if you take 1 divided by a really big number, that's getting really close to 0. And the tangent of 0 is 0. So this is infinity times 0. And it really seems like infinity times 0 should be 0. It's not. Well, it might be, but it also might not. Okay, so I can come up with a scenario where infinity times 0 is 2. And I can come up with another scenario where infinity times 0 is 7. So when you get infinity times 0, you know nothing. This has come up a few times. I know specifically, maybe a month ago, I talked to Michael about it, because he was wanting to put down 0 for infinity times 0. I said, that just doesn't work. Okay? So infinity times 0 is indeterminate. You don't know anything, just like 0 over 0 and infinity over infinity. So what we're going to do when we get infinity times 0 is we're going to, instead of multiplying by x, we're going to divide by 1 over x. Is that okay? Am I allowed to do that? Dividing by 1 over x, same as timesing by x? Yeah, all I'm saying is if you divide by a half, it's the same as times 2. Or if you divide by a third, it's the same as times 3. Okay, so the reason I did that is now we've got 0. We already did tangent of 1 over x, and we said that was getting close to 0. And then 1 divided by a really big number is getting close to 0. So if we reframe the question like that, then we're getting 0 over 0. And that's good because then L'Hopital's rule applies. Okay, so to make this easier, I'm going to rewrite this as tangent of x to the negative 1. That's what 1 over x is. Still 0 over 0. I didn't change anything, just rewrote it. So 0 over 0 applies. We're getting 0 over 0, so L'Hopital's rule applies. So now I'm going to take the derivative of the bottom and the top separately. There's the derivative of the bottom. Derivative of tangent is secant squared. But then there's a chain rule. Then that's nice because these are going to cancel. So I've got the limit as x goes to infinity of the secant squared of 1 over x. One divided by a really big number is getting close to 0. So we're close to 0. Secant is 1 over cosine. And the cosine of 0 is 1. So if this is getting close to 0, then this is getting close to 1. And then 1 squared is 1. So answer to this limit is 1. One divided by a really big number is getting close to 0. So we're taking this secant of something close to 0. That's 1 divided by the cosine of something close to 0. Cosine of something close to 0 is close to 1. 1 divided by 1 is 1. 1 squared is 1. Good. Okay, so that's that answer. Let's try. Okay, so we got to take the secant of pi over 2. So here's our unit circle. Pi over 2 is up here. This is 0, 1. So we're getting close to 0. Sorry, secant is 1 over cosine. So we're taking something 1 divided by something close to 0, and that's going to infinity. So this is going towards infinity. And then the tangent of pi over 2 is 1 divided by something close to 0, which is infinity. So tangent of pi over 2 is going to infinity as well. So this time we're getting infinity minus infinity. Seems like infinity minus infinity should be 0. It's not. You just can't do math with infinities in the same way that you do math with numbers. It just doesn't work. Okay, so what you do when you get infinity minus infinity is you get a common denominator. When you have infinity minus infinity, get a common denominator. And secant is 1 over cosine. And tangent is sine over cosine. So if you frame the problem that way, you really have a common denominator already. But there might be a different problem where you have to do some math to get the common denominator. Okay, so this is 1 minus sine over cosine. Okay, sine of pi over 2 is 1, and 1 minus 1 is 0. So the top's coming out to 0. And the cosine of pi over 2 is 0. So the bottom's coming out to 0. And that's good news because that means L'Hopital's rule applies. So I take the derivative of the top. Derivative of sine is cosine. And the derivative of the bottom. Derivative of cosine is negative sine. Then cosine of pi over 2 is 0. Sine of pi over 2 is 1. So final answer is 0. So this time it turns out infinity minus infinity was 0. But that's not a universal fact. There could be a different infinity minus infinity which would come out to 7. There could be a different one that came out to 2. Everybody doing okay? Okay, then there's something I need to say to everybody. The cal that's due tomorrow, you need to use your calculator to solve the equations. Like you're going to get some equations that look crazy nasty, like e to the x times x over 28 equals sine of x plus 1. Do not try to solve these by hand. The directions even say, this is calculator active, it involves equations that you're going to... So how do you solve an equation with your calculator? Put one of the sides into y1 and put the other side into y2 and then calculate the intersection point, right? We've done that, but people forget to do it. They're so trained to solve stuff by hand that they forget to do it. So that happens, I think, virtually on every problem on the calc. So don't despair if you're getting a big mess that you can't solve. Just use your calculator to solve it.